Hello students, in today's class we are going to study about the second element of the group 15. So as you know, group 15 element is well known by the name nitrogen family. Why? Because the oxides formed by the group 15 elements are acidic in nature and they are very suffocating. So the second element of this nitrogen family is phosphorus. So phosphorus is having the atomic number 15 and mass number 30. The general valencies are 3 and 5. So phosphorus exists in different allotropic forms such as white, red, black, and besides these there are so many other forms like scarlet, violet, and but in this class we will study only about first three allotropes of the phosphorus. So if we look back into the history of this element, then we will come to know that in the early time, white phosphorus was widely used to make the matchsticks and lighting the fire. But it was not the appropriate solution for this problem, as the white phosphorus catches fire easily on exposure to the air. Moreover, the laborers working in such industries come in the direct exposure to the phosphorus because they were not using any PPE that time, and they becomes the victim of the deadly disease known as Foshi jaw disease, means the extremely necrosis of the jaw and the skull bones. So after this historical perspective, I would like to ask you one question, that what is the chemical reaction behind when the matchstick is just rubbed over the matchbox and it starts burning? We all know it very well that nowadays black phosphorus is generally applied over the heads of the matchsticks, and matchbox are provided with red phosphorus along with a mixture of the glass powder over the sides of the matchbox. So when we strike the matchstick over the side of the matchbox, then due to the force of the friction, heat energy is released, and some of the red phosphorus in the matchbox turns into white phosphorus. And we all know that white phosphorus has the tendency to catch fire, so it immediately ignites the matchstick, and that's why this matchstick burns. So now let us start our topic with the sources. The main source of the phosphorus in nature is from the crystals of apatite family. The chemical formula is calcium phosphate and calcium X2, where X may be chloridine, fluoridine, or hydroxyline. If it is chloridine, then we call the crystal as calcium chloroapatite. If it is fluoridine, then we call the crystal as calcium fluoroapatite. And if it is hydroxyline, as the constituent of our enamel, then we call it calcium hydroxyapatite. So we know it very well that our tooth enamel is one of the hardest substance in our body, but it is also gets demineralized when we take the sweet substances and microorganisms and the bacteria in our body that takes that sweet substances left in the mouth and hydrolyze them into strong mineral acids, and these acids just causes the demineralization of the tooth enamel. Other sources of phosphorus is milk and eggs. Phosphorus is also present in the bones and also in the cell membrane. It is also the main constituent of the nucleic acids in the form of phosphate groups in case of DNA and RNAs, etc. We have also heard that ATP is the currency of energy at cellular level. So energy is stored in the form of these phosphorus containing phosphate groups. When 1 mole of ATP converts into ADP by hydrolysis. There is a release of 30.5 kilojoule of energy. Then comes the uses of phosphorus. Phosphorus is widely used in making the matchsticks, fertilizers, main nutrients for the plants, and rocket fuel. The radioactive phosphorus is also used as tracers to study the mechanism of the chemical reactions. Next is the phosphorus bombs. But these bombs are so dangerous that causes the death of very innocent civilians. So on the humanitarian ground, these are banned nowadays after the Geneva Treaty 1980. Phosphorus is also used for making the important compounds like phosphorus trichloride, phosphorus pentachloride, phosphine gas, and many other oxoacids of organic compounds containing the functional group like hydroxyl. Whereas it is also used for making the very poisonous gas like phosphine and oxoacids like phosphorus acid, phosphoric acid, etc. So when we see the etymological meaning of the word phosphorus, in Latin, the word phos means light and the word forus means bringing. So phosphorus is a substance which brings the light when exposed to the air. White phosphorus is the basic form of the phosphorus, in which P4 molecules exist in the form of tetrahedral structures. So when this white phosphorus is heated at a temperature of 573 Kelvin in the inert atmosphere of carbon dioxide for several days in a sealed tube, then red phosphorus is formed. So in this way, large number of P4 molecules gets polymerized to form long chain of red phosphorus. This red phosphorus is relatively more stable than the white phosphorus, but upon heating it again sublimes into white phosphorus. Means some part of this red phosphorus again gets converted into white phosphorus for the moment, and it gets readily oxidized in the air, forming the phosphorus pentoxide with dense white fumes. After this, when the red phosphorus is heated at a temperature of 803 Kelvin in a sealed tube under high pressure, then it transforms into another allotrope, that is black phosphorus. But the black phosphorus is again of two types. The black phosphorus that we derive from the red phosphorus is called alpha black phosphorus. It has honeycomb-like structures like that of graphite. But main point to remember here is that it is not a good conductor of electricity like the graphite. Now finally the beta black phosphorus. Beta black phosphorus is a good conductor of electricity. Its structure is quite similar to the alpha black phosphorus, and it is prepared from the white phosphorus by heating it at a temperature of 473 Kelvin. The top view of the structure is honeycomb-like, but when we see the side view of the structure, it looks like the plated structure or quite resembles with the chair form conformation. So in this way you can see here that one form or allotrope of the phosphorus can be easily transformed into another type of allotrope. White phosphorus. Sometimes white phosphorus is also referred as yellow phosphorus because on exposure to air it easily gets oxidized into yellow color solid. It has a characteristic garlic-like smell. It is very poisonous. When we see the structure of the white phosphorus, we find that it consists of 4 phosphorus atoms joined together in a tetrahedral structure. Each phosphorus atom is bonded to 3 different phosphorus atoms, and there are total 6 single bonds in the whole P4 molecule. The angle strain is very high, that is 60 degree, which makes it very reactive. It easily catches fire in air because it easily gets oxidized into phosphorus pentaoxide with the release of heat and dense white fumes. It has the property to glow in the dark. Therefore, sometimes it is also referred as devil's element. It is stored under water because it easily gets oxidized by the air. It is not soluble in the water, but it is soluble in hot aqueous solution of sodium hydroxide and other organic solvents like carbon disulfide. Now the second allotrope of phosphorus, that is red phosphorus. It is a solid with gray luster. It is odorless and non-poisonous in nature, like the white phosphorus. As the red phosphorus is formed by heating the white phosphorus at a temperature of 300 degrees centigrade, or we can say 573 Kelvin, so large number of P4 molecules gets polymerized and forms a long linear chain of P4 molecules. That is called the red phosphorus. In the structure, we can find that each phosphorus is making the 3 bonds with other phosphorus atoms. So, from the structure of the red phosphorus, we can find here that angular strain is less. So, it imparts it more stability. Its stability is quite large than the white phosphorus. Due to this large stability, it is less reactive and it does not catches fire in the air like the yellow phosphorus or the white phosphorus. It has no characteristic property of chemiluminescence, means glowing in the dark. It is insoluble in the water but soluble in the organic solvents like carbon disulfide. Now the third allotrope of the phosphorus, it is black phosphorus. It is the most stable allotrope of the phosphorus. It exists in mainly 2 forms. One is the alpha black phosphorus and the other one is beta black phosphorus. As you can see here that alpha black phosphorus, it is insulator, but the beta black phosphorus conducts the electricity. Therefore, it is also used for making the semiconductors used in different electrical appliances. Black phosphorus is highly dense, hard, and highly polymerized solid with black luster. It possesses pleated honeycomb-like structure. Pleated means the structure of the rooftop seats, which allows the rainwater to move downwards. It is non-poisonous in nature like the white phosphorus, and it does not possess any characteristic odor. So in the honeycomb structure you can see that there is least angular strain, which enables the black phosphorus is the one of the most stable allotrope of phosphorus. It is least reactive and does not catches fire, so it is not placed under water like the white phosphorus. It is not soluble in the water as well as in the organic solvent like carbon disulfide. Moreover, it does not possess the characteristic of chemiluminescence, means glowing in the dark. So this was all about the 3 allotropes of the phosphorus. Now let us start with the first compound of the phosphorus, that is phosphine. Let us begin with the preparation of the phosphine gas. It is prepared by the reaction of calcium phosphide with the water. There is the formation of phosphine gas with a rotten fish-like odor. The other way of preparation is by reacting the calcium phosphide with the acid HCl. There is again the formation of the phosphine gas. But in the laboratory, we can prepare this phosphine gas by dissolving the white phosphorus in boiling alkali solution, that is sodium hydroxide solution. And there is formation of phosphine gas along with the other byproduct like sodium hydrogen phosphide. Now next is the properties of the phosphine gas. Phosphine is a colorless gas with rotten fish-like odor. It is non-flammable gas but explodes violently in the presence of phosphorus vapors or phosphine. Phosphine, just like the alkane, if the phosphorus is there in case of carbon, it is called phosphine. The simple formula is P2H4. And the presence of oxidizing agents like nitric acid, chlorine, and bromine, etc. Phosphine is highly soluble in the water and weakly basic in nature. Phosphine gas prepared by the above method is further purified by absorbing this gas in the hydrogen iodide, which forms phosphinium iodide. This phosphinium iodide is when reacted with the potassium hydroxide solution, it forms potassium iodide along with the release of pure phosphine gas. Now next is the reactivity of the phosphine gas with metal solutions. Phosphine gas reacts with the metal solutions like copper sulfate and forms cupric phosphide along with the formation of sulfuric acid. When the mercury chloride is reacted with the phosphine gas, there is the formation of mercuric phosphide along with the formation of hydrochloric acid. Now the uses of phosphine gas. Phosphine gas is used mainly in Holmese signals. Holmese signals are the SOS signals. SOS means save our soul. Safety signals which are used during emergency while shipwreck or any other situation. During this, the tin containers containing the calcium carbide and the calcium phosphide are purged and thrown in the water. While reacting with the water, they forms acetylene gas and phosphine gas. When they come in close contact with each other, they form dense white fume and smoke. And this smoke is visible from many kilometers far away. Similarly, the phosphine gas is also used during warfield for making the smoke screens in order to protect ourselves from enemies. Halides of phosphorus. Phosphorus mainly forms two types of halides, that is px3 and px5, having the oxidation state of phosphorus plus 3 and plus 5. In the plus 3 oxidation states, phosphorus combines with fluorine, chlorine, bromine, and iodine. Whereas in the plus 5 oxidation states, it is possible only with the fluorine, chlorine, and bromine. Means due to the less electronactivity of the iodine, it cannot form plus 5 oxidation compound with the phosphorus. So let us start with the preparation of phosphorus trichloride. It is the first halide of phosphorus. So when white phosphorus is reacted with the chlorine, it forms PCl3, easily forms the phosphorus trichloride. Similarly, phosphorus can again be reacted with thionyl chloride. There is again formation of phosphorus trichloride along with the formation of byproducts like sulfur dioxide gas and disulfur dichloride, or it is also named as sulfur monochloride gas. Structure of phosphorus trichloride. We can see here that phosphorus trichloride possesses pyramidal structure along with the lone pair of electron with the phosphorus atom. Next is the properties of the phosphorus trichloride. It is colorless oily liquid and readily hydrolyzed by the moisture. When it is readily hydrolyzed by the moisture, there is release of dense white fumes of hydrochloric gas along with the formation of phosphorus acid, that is H3PO3. Phosphorus trichloride is also very good halogenating agent, and therefore it reacts with the organic compounds containing OH hydroxyl group as a functional group and replace it with the halogen atom. So when ethanol is reacted with phosphorus trichloride, there is the formation of ethyl chloride with the release of phosphorus acid. Similarly, when acetic acid, which contains OH in the terminal part of the functional group, reacts with the phosphorus trichloride, then it results in the formation of acetyl chloride along with the formation of phosphorus acid. So dear students, like the phosphorus trichloride, now the next halide of phosphorus is phosphorus pentachloride. Phosphorus pentachloride is prepared when the white phosphorus is reacted with excess of chlorine and there is formation of phosphorus pentachloride. The second method of preparation of phosphorus pentachloride is when the white phosphorus is reacted with sulfuryl chloride. There is formation of phosphorus pentachloride along with the formation of sulfur dioxide. As you can see from the balanced chemical reactions given here. Now let us discuss the structure of phosphorus pentachloride. In the liquid and the gas phase, phosphorus pentachloride possesses trigonal bipyramidal geometry, in which the axial bonds are quite longer than the equatorial bonds. This is because of the reason that two axial bonds are repelled with greater force by three equatorial bond pairs. Now, the properties of phosphorus pentachloride. It is a yellowish white powder which is easily decomposed by the moisture into phosphorus oxychloride and hydrochloric gas. So this phosphorus oxychloride gets further hydrolyzed into phosphoric acid with the release of large amount of hydrochloric gas which produces dense white fumes. So secondly, when the phosphorus pentachloride is heated, it easily gets decomposed into phosphorus trichloride with the release of chlorine gas. Dear students, like phosphorus trichloride, phosphorus pentachloride is also a good halogenating reagent. So it reacts with many of the inorganic as well as organic compounds containing the OH group as a terminal part of the functional group and converts them into halogen compounds. So let us take the first example with the ethyl alcohol. When ethyl alcohol is reacted with the phosphorus pentachloride, there is formation of ethyl chloride, that is alkyl halide, along with the formation of phosphorus oxychloride and hydrochloric gas. Similarly, take another example. Now we are taking the example of acetic acid, that is ethanoic acid. So this is the 2 carbon containing carboxylic acid which is well famous by the name of vinegar. So when this compound reacts with the phosphorus pentachloride, there is formation of acetyl chloride and phosphorus oxychloride and hydrogen chloride gas. Action of phosphorus pentachloride towards finely divided metals. So when phosphorus pentachloride reacts with the finely divided metals like silver and tin, there is formation of their metal salts in the form of metal halides. Specifically, we can say silver chloride and tin tetrachloride, along with the formation of phosphorus trichloride. So, in the solid state, phosphorus pentachloride exists in the ionic form, in which there is phosphorus tetrachloride as a cationic part and phosphorus hexachloride as an anionic part. So, in the cationic part, the geometry is tetrahedral, whereas in the anionic part, the geometry is octahedral. Now, the next topic is oxoacids of phosphorus. As we can see here from the table, detailed information of 7 oxoacids have been given here. The first of which is hypophosphorus acid with the chemical formula H3PO2. Here the oxidation state of phosphorus is +1, and the method of preparation, it is mentioned here that we can prepare this hypophosphorus acid by reacting the alkali metal with the white phosphorus. So while analyzing this table, one thing is very clear that in every case, phosphorus will make 5 bonds, and out of which one bond will be phosphorus and hydroxyl bond, and the one bond is phosphorus double bond with oxygen. So in this case, every phosphorus will make the 3 bonds pre-decided and 2 bonds are different, that depends on structure to structure. So these are the some of the structures of the oxoacids taken from the NCERT book, but let us discuss each of them one by one. So the first case is hypophosphorus acid. In this case, the formula is H3PO2, and we can find here that the oxidation state of phosphorus is +1. So +1 is the lowest oxidation state, whereas in other case we can find that oxidation state of phosphorus is +3, +5 and +5. So as I have told you earlier that one of the bond will be phosphorus double bond oxygen, it is pre-decided, and other bond is phosphorus single bond with the hydroxyl group, that is OH group. So it is pre-decided. So now the 3 bonds of the phosphorus is complete, and we have the 2 hydrogen left, as we can see from the formula H3PO2. So these 2 hydrogen atoms will directly get linked to the phosphorus atom by single bonds. So in this way we will have 5 bonds of the phosphorus with different elements. So from this structure, we can conclude about the basicity, reducing character, oxidizing character, and reversible reaction. The basicity of this acid depends upon the ionizable hydrogen that is associated with the number of OH groups directly linked to the phosphorus atom. So in this case, we can find here that only one OH group is directly linked to the phosphorus atom. So its basicity is 1. Next case is the reducing character. Reducing character depends upon the number of hydrogen directly linked to the phosphorus. So as I have mentioned here, the 2 hydrogens encircled with the red color ink, they are directly linked to the phosphorus, and they imparts the reducing character to the oxoacid. So it is having 2 pH bonds directly linked, so it is having the highest reducing nature. No any other acids have such an conditions. Some other oxoacids have 1 pH bond and others have no any pH bond. Now the oxidizing character. It does not have any oxidizing character because here the central atom, that is phosphorus, it is in the lowest oxidation state. It cannot further oxidize other element to decrease its oxidation number below +1. Moreover, it can increase its oxidation number from +1 to +3 or more. Now the next is disproportionation reaction. Hypophosphorus acid does not undergo disproportionation reaction. Now the next acid is phosphorus acid. It is having the formula H3PO3, and we can find here that the oxidation number of phosphorus is +3. So it can be prepared from diphosphorus trioxide by its hydrolysis, or we can prepare it by the hydrolysis of tetraphosphorus hexoxide with water. So in this way we get phosphorus acid. So after this, let us come to the structure of the orthophosphorus acid. So in the structure we can see here that phosphorus is the central atom, and in which phosphorus double bond oxygen is pre-decided and one phosphorus single bond OH is further pre-decided. So in this way three bonds are pre-decided. Now if we compare our half-made structure with the chemical formula, then we will come to know that still two hydrogen and one oxygen is remaining to be bonded with the phosphorus. But there is a condition that phosphorus only makes 5 bonds. So we have to join one hydrogen directly with the phosphorus and the remaining oxygen and hydrogen in the form of hydroxyl ion. So in this way we can easily prepare the structure of orthophosphorus acid, or simply called as phosphorus acid. So let us draw some information from this structure. If we compare the basicity of this orthophosphorus acid, it will come about to be 2, because we are having two ionizable hydrogen directly linked with the oxygen. So if we want to compare the reducing character of this acid, we can see here that one of the hydrogen that is directly linked to the phosphorus, and it is having some reducing power but less as compared to the previous acid that we had discussed, hypophosphorus acid. Now the next oxoacids of phosphorus, in which phosphorus possesses +3 oxidation state, is pyrophosphorus acid. As the name suggests, pyro means heating. So it is clear that it is obtained by heating the orthophosphorus acid. So this pyrophosphorus acid is prepared by heating orthophosphorus acid, that is H3PO3, with phosphorus trichloride and water. So it leads to the formation of pyrophosphorus acid, which is having the formula H4P2O5. Now we can see from the formula that there are two phosphorus atoms, but oxygen is present in odd number. So the one extra oxygen that will bridge the two phosphorus atom together. So in this way 90% of the structure is constructed in our mind. Each phosphorus atom will make total 5 bonds. So firstly, one of which will be with the bridging oxygen. Secondly, each phosphorus atom will make a double bond with the oxygen. And thirdly, each phosphorus atom will make a single bond with the hydroxyl ion, that is OH. So now when we compare our half-made structure with the chemical formula, that is H4P2O5, then we come to the conclusion that we have bonded all the atoms to the phosphorus atom, but we have left only two hydrogen atoms to be joined to the phosphorus atom. attach or bond one of the hydrogen with each phosphorus atom, and with this our structure gets completed. So this is an easy trick to learn how to draw the structures. One more thing must be kept in mind, that when we see the suffix OUS, then the oxidation state of the oxoacid is always +3. But in case of hypophosphorus acid, it is less than +3, that is +1. Now the case of phosphoric acid. So firstly start with the metaphosphoric acid. Metaphosphoric acid is having a general formula HPO3 as a monomeric unit, which gets polymerized in the cyclic way or the linear pattern to give rise to different cyclic metaphosphoric acid or polymetaphosphoric acids. So how this metaphosphoric acid is prepared? So dear students, when phosphorus acid, whose formula is H3PO3, is reacted with the bromine and heated in the sealed tube, then we get metaphosphoric acid. So you can draw the structures of these tricyclometaphosphoric acid and polymetaphosphoric acid using the given conditions, that each phosphorus atom will make the 5 bonds, one of which will be phosphorus oxygen double bond, one will be phosphorus single bond OH bond, and other 2 left bond will be with the 2 left out oxygen atom. But these bond will be single bond, and as these oxygen atoms are in the chain or in the cycle. So after this, the next oxoacids of phosphorus is phosphoric acid. It is having the formula H3PO4, in which the central atom phosphorus is having +5 oxidation state. It is the highest oxidation state, as in case of metaphosphoric acid we have recently discussed. Now, in order to make the structure of phosphoric acid, we will use the same trick. That is, phosphorus will make a double bond with the oxygen and a single bond with the OH group. Now we will compare the half structure with the chemical formula, that how many hydrogen and oxygen we have left to be bonded with the phosphorus atom. So we have come to the conclusion that we have left 2 hydrogen and 2 oxygen atom remaining to be bonded to the phosphorus atom. But as we have seen that 3 bonds have already made, so there is requirement of only 2 bonds that can be made with the phosphorus. So we will join these 2 oxygen and 2 hydrogen in the form of OH bonds directly with the phosphorus atom. So in this way we will make the complete structure of phosphoric acid. So after this, let us discuss the structure of phosphoric acid. We can see here there are 3 OH bond directly linked to the phosphorus atom. So in this way there are 3 ionizable hydrogen, and the basicity of this phosphoric acid is 3. So when we compare its reducing character, we can find here that there is no any hydrogen that is directly linked to the phosphorus. So it is not reducing acid, but it is oxidizing acid. Phosphoric acid does not exhibit any disproportionation reaction because it is already in the highest oxidation state, so it cannot increase its oxidation state beyond 5. Now let us discuss the another oxoacid of phosphorus, that is pyrophosphoric acid. So as the name suggests, it is derived by heating the phosphoric acid and we get this one. The formula is H4P2O7, but the oxidation state is same as that of phosphoric acid. So it is +5. From the formula of the pyrophosphoric acid, we can conclude that oxygen is not present as an even number. It is present as odd number. 7 is the odd number. So there will be again the presence of phosphorus oxygen phosphorus bridging bond. So dear student, now utilize the same previous trick I have told you to draw the structure of the pyrophosphoric acid. So the first condition is phosphorus will make the 5 total bonds, one of which is phosphorus oxygen phosphorus bridging bond. Second trick you can use is join oxygen atom with each phosphorus by double bond and hydroxyl group with each phosphorus atom by single bond. So in this way you can see that half of the structure is ready. Now count the number of atoms in the half made structure and with that of formula. We can come to the conclusion that the number of hydrogen is 2 and number of oxygen is 2, which we have to attach to the each phosphorus atom. So now we will attach these atoms in the form of OH bond with the phosphorus, because 4 bonds are already made, so there is capacity of the phosphorus to make only one new bond. So that bond will be in the form of phosphorus dash single bond with the OH group. So in this way the structure of pyrophosphoric acid is now complete. So dear student, now the last structure of oxoacid is hypophosphoric acid. It is having the formula H4P2O6 and the oxidation state of phosphorus is here +4 oxidation state. But there is one new thing here, that oxygen is present here in the even number. So there will be no phosphorus oxygen phosphorus bridging bond, and instead there will be a direct link between the two phosphorus atom as P-P bond. So let us discuss how this hypophosphoric acid is prepared. So in the preparation part we come to the conclusion that when the red phosphorus is heated with the alkali metal, any alkali metal like sodium or the potassium, we get this hypophosphoric acid. So finally let us discuss the structure of this hypophosphoric acid. So dear students, we know that in the formula there are the two phosphorus atoms, so we will join them with a single bond. Now with each phosphorus atom we will attach the oxygen atom by double bond and one OH group with a single bond, as we are doing in the all previous tricks. So now we will count the number of oxygen and the hydrogen in the structure as well as with that in the given formula. So we have come to the conclusion that there are 2 oxygen atom and 2 hydrogen atom left to be bonded to this structure. So now we will count the number of bonds already made by the phosphorus. It is 1, 2, 3 and 4. So there is capacity of the phosphorus to make only one new bond. So we will attach the oxygen and hydrogen in the form of OH, that is hydroxyl group with the phosphorus. So it will require only one single bond to attach one hydrogen and oxygen together with the phosphorus. So in this way we can attach two OH groups with the phosphorus by single bonds with each. Now discuss about the basicity of this hypophosphoric acid. So depending upon the number of ionizable hydrogen or the OH groups directly linked to the phosphorus atom, we can say here that there are 4 ionizable hydrogen, so its basicity is 4. So with this now I am finishing my video. Thank you students for listening me patiently. Thank you very much.